In the video, we saw a little car go zoom. Let's simplify the car to just an object. And let's simplify all the forces acting on the car to just one net force causing the car to move to the right. We know that there would be a gravitational force acting on the car, and that there should be some normal force from the floor back up onto the car, but overall, in the horizontal direction, there's some net force that's acting on the car to cause it to go. So now the car goes, and the spring is engaged in the little pullback car for a particular amount of distance and time, but something we can measure would be distance. So if we were to create a graph of the force, the net force over the position here, and let's just, again, simplifying our problem, say that our net force on the car was constant for this change in position. Now, the net force acting on the system would cause the mass to accelerate. Now, what does acceleration mean? Acceleration indicates there will be a change in velocity, and this change in velocity will occur over time, and there'll be a change in position of the object. So if we go back to kinematics, there was a final velocity squared was equal to our initial velocity squared plus 2a delta x. So I can relate velocity and initial velocity and position to the acceleration. And so I can think of my net force then as causing this mass to have a change in velocity over a change in position. So if we look at this equation that we have written here, and we look at how we graphed this force that was acting on the object and with respect to its change in position, I know that a force or a vertical component, vertical axis times the horizontal axis, would give me the area under this curve. So if I rearrange this equation here and say, well, the net force times the delta x will be equal to m times v squared minus v initial squared over 2. And then, really look at that, and well, that would just be mv squared over 2 minus mv initial squared over 2. And that's what occurs when there is this net force that's acting on the system through a change in position. So what is this? Well, when the force acts through a distance, the velocity changes. And this object went from not moving to moving. And so the force caused a change. This force that acted over a distance, through a distance, caused a change. And so that negative sign, final minus initial, indicates a change. Then this component here that is mv squared divided by 2, or more familiarly, 1/2 mv squared, we refer to as the energy that is stored in the movement, and movement is kinetic. Okay, so the kinetic energy. So the object wasn't moving to begin with, it was at rest, and then it started moving and it went through a change in velocity, and that change was due to this force that was applied to it over this distance or through this distance. And so whenever we apply a force through a distance, we refer to that as the work, okay? The work. And so mathematically, what I see here is that the area under the curve up here is what we're calling, in terms of physics, the work. And now what does that work represent? What does it mean? Well, looking back down here, if this expression is 1/2 mv squared, which is referred to as my energy due to the motion, the moving, then this work is equal to a final energy stored in the motion minus an initial energy stored in the motion, or kinetic energy. So the work done by this force on our object causes a change in the kinetic energy. Now let's look at units. Work would be a force, Newton, times a meter, and therefore the unit for this energy would be a Newton times a meter, Newton meter. But because of the scientist James Prescott Joule, we call a Newton meter a joule for James Prescott Joule, where J is our abbreviation. And so that is our unit for energy as well. So our energy stored in the motion of an object can be calculated by 1/2 mv squared. That's very important. And kinetic energy is the only kind of energy that a single object can have. An object can have kinetic energy. Let's look at this idea of work a little more in depth. So we started out with the fact that we had an object and we simplified all the forward forces to being a net forward force. And, it did have a gravitational force acting on it. It does have some sort of normal force acting on it. But we simplified this forward force, and we looked at how that forward force was causing the object to have a change through a distance, and that distance was parallel to that force. So when we think about summing the forces on an object, and let's say, for example, it's like something we're pulling, like a sled or a wagon or something like that. We have a force that's maybe pulling, or we're pulling along a string or a handle or something. And here's a gravitational force, and here is a normal force, and this is the x direction. Now, as you pull this object along the floor and you pull it through some change in horizontal position there, and we're looking at the sum of the forces in the x direction, we would have that this force pull at some angle, so force pull cos theta, would cause the mass to have an acceleration. And so it's actually this component of the force that is causing the acceleration. And if I go back to my earlier derivation where I had force and then cosine theta, and then remember the acceleration could be written as v squared minus v initial squared over 2 delta x, then your force pull times the cosine times the delta x would give us our 1/2 mv squared minus 1/2 mv initial squared. So simply, this force is the component of the force that is parallel to the distance times this change in position or change in distance, and that causes this change in kinetic energy or energy stored in the motion. And if we kind of go back to what is a force is actually a vector. And our change in position is actually a vector, a direction. And if you take two vectors, and if you remember from your math class, if you have two vectors and you take the dot product of those vectors, then it's the magnitude of the vectors times the cosine of the angle between the two vectors. So this notion of work is that it is really the dot product of the force and the position vector. So overall, what we get is that the work done by a force is the dot product of the force and the change in position or the position vector, and that would be the force that is parallel to the change in position. So the cosine, if you have the angle between x and the force, times x, and that work causes a change in kinetic energy. Now, the way to make this really hit home is that let's think about what happens to the little car as it comes rolling to a stop. Okay, so our little car is moving along and it's going to come to rest. Now, what force would be acting on this car to possibly cause it to slow down? That might be like a friction force. And the friction force, we know, would be opposing the motion. And it's still on the Earth, so there's a gravitational force and there is a force from the surface, a normal force. Now in this case, as the object goes to the right, so we've got this change in position to the right, this frictional force is acting in the opposite direction. So we have to be careful and think about our vectors. And so the work done by this force of friction would be the force of friction, which is negative, times the change in position. You think about what that means in terms of the energy. This would be a negative value. This is going to be equal to our change in kinetic energy. And if you think about it, your change in kinetic energy is your final kinetic energy minus your initial kinetic energy. And if our final kinetic energy is 0 because we've stopped, and our initial kinetic energy is something non-zero because it was going to begin with, then there was a negative change in energy. So work changes the energy of a system.